Greetings, everyone. Welcome to the AI Files, your ultimate destination for staying updated on all things artificial intelligence. We dive into the latest developments in the AI world, sharing insights from the corporate landscape. We also bring on expert guests to provide their unique perspective. You can find us in both the Apple Podcast as well as YouTube channels. If you're serious about keeping up with the fast paced world of AI and want to integrate its advancements into your career and company, then this is the podcast for you. I am Shadab Hussain, co host of the AI Files. I'm the director of data and AI at Microsoft with over 22 years of experience in the analytics and AI field.
And I'm Jamie Basilico, co-host of the AI Files. As a data and AI technical specialist and architect, I bring over 35 years of experience in data-related and AI domains, having worked with many Fortune 500 companies throughout my career. Please note, this is not an official Microsoft channel. The views and opinions expressed by the co-host are their own and do not represent the views of Microsoft. Let's dive in.
The present era of AI has been revolutionized by generative AI, powered by large language models or LLMs. Before LLMs, AI was an elite technology that required humans to communicate in AI's language. Now, with LLMs understanding and speaking human language, AI has become accessible to everyone, transforming numerous fields. Without the ability to understand natural language prompts, generative AI would not be as popular or effective as it is today. But what exactly is an LLM? How does it work? What are parameters, prompts, or context? How does it comprehend natural language? And there are many more questions to explore.
To help us understand these concepts, we've invited a brilliant engineer to share his insights. Today, we're thrilled to have Simon Lacasse with us. Simon is a global black belt of artificial intelligence at Microsoft, a title and honorific that signifies the depth of his expertise and experience in AI. This episode is packed with valuable information, so we've actually broken it into two parts. Both parts will have advanced aspects that we'll cover, and real world applications of large language models, providing you with a comprehensive understanding of this transformative technology. So let's dive in and bring Simon on stage.
And we have an eminent guest today. Simon, we are so honored to have you on the podcast today. Why don't you introduce yourself?
Hello everyone. My name is Simon Lacasse. I'm part of a team called the Global Black Belts, the AI Global Black Belts at Microsoft. And it's not that we know karate or wear a black belt, but essentially we are deep experts in AI, and we help our customers democratize and use AI across the Microsoft Azure platform.
Perfect. Thank you so much, Simon, for your time and joining us today. You are actually the first guest, so you are always going to be special for this podcast. Um, Here's the thing, Simon, I want to actually really talk about today. And today our topic is, talking about large language models and, all about them. But AI has existed, right? In my experience of 22 years in the data and AI, it has always existed. Um, why does it feel like that it is just born yesterday? Why so much focus now? Why has it not been that effective earlier? What has changed really?
Yeah, I would really love to know that answer as well. I mean, when I start getting relatives and friends that are non-technical start to talk about things like chat GPT and what can it do, I know it's kind of like hit this boiling point or that's tipping point. So very interested in your thoughts, Simon, around like why now? Like what's changed in terms of mindset of people?
Yeah, that's a great question, and I think you're kind of putting me on the spot here on the first question, but it's a good question, and I think I mean we can be technical about it, and we can say that it has a lot to do with things like deep learning and transformer models, and we will talk about that later on when we talk about LLMs more specifically. But I think from a general perspective, you're absolutely right, Shadab. I think we had AI is not new. We've been doing AI for a very long time. I think what's really changed is like when we used to do like more narrow AI, like traditional AI, the models were small, right? And like we were able to use these models and use a small amount of compute to run kind of more narrow workloads. And I think now there's an explosion in data, right? There's so much data everywhere, and we now have the ability with things like GPUs and CPUs that have exponentially gotten faster and have giving us the ability to process a lot more information. We have the ability now to create these really, really large models, right, that can consume this data and then create a model out of that. And these very large models, if you look at models like GPT-3, GPT-4, they have billions of parameters, right? And we'll talk about parameters a bit later, but they're huge models, and we have the ability to take all that data and create these really big models using things like distributed learning to be able to really train these humongous models. And what that does, it gives these models the ability to do a lot of things, right? Like if you look at a GPT-3 model, it's not just a model that can do sentiment analysis, but it can do entity recognition. It can summarize, right? It can do a lot of things because this model has basically been trained on a very large portion of the internet, right? So now you have kind of a replication of the internet into a model that you could use to make predictions around language, for example. And I think that's why we're seeing a lot of this, right? Like when you look at a model like ChatGPT, it's a model that's been trained on a lot of data. It's a very big model, and people can use it and they can interact with it using natural language because these models are so good at being able to understand language that we don't really need to code this stuff anymore, right? We speak to them, we use natural language, and they're pretty smart because they've learned a lot about language and they can do quite a lot of things. And I think that's the shift that we're seeing. When somebody is using ChatGPT, you can use ChatGPT to do a lot of things, right? You can ask it questions, you can do summarization, you can, bring in new knowledge to make it reason over that knowledge. So I think this is where we're seeing a significant shift where you have these, large language models, but that can be used universally for a lot of use cases. And I think that's the big difference that we're seeing right now.
And I guess that this is where I'll go with maybe my first question for you is, you just mentioned a large language model, but like at its crux, what is a large language model, and why is that so different, I guess, in my own head, between the old, quote unquote, old machine learning algorithms that may be very specific in terms of doing a task, but how does that compare to a large language model? And why is a large language model in and of itself good at doing more than just a specific task? It seems like it's good at doing just about anything that you could think up of a task for. It could, I don't want to say it's going to do everything, but it seems like it could do more than just a very specific task. And it seems like it's a general model. And my question would be, how does it do that? Like, what is the large language model in its crux? Then how does it really work in the first place to allow it to do those things that you probably would have needed, 4 or 5 or 10 or 12 different very focused models or algorithms to do the work?
Yeah, well, the reality is it's actually not that much different than the traditional kind of machine learnings that we used to do in terms of the the algorithms. But of course, the models, the architectures, the way we develop them has been very different. And the way I like to think of an LLM, it's kind of like a giant super smart calculator, but instead of trying to solve math problem, it solves puzzles in language, right? And just like a calculator can predict the answer to a math question, an LLM can predict words, but it can also predict sentences and paragraphs. So, for example, let's say you type in a number in an operation in a calculator. The calculator uses its rules in mathematics to give you an answer. Similarly, an LLM uses the rules and patterns of language to predict and generate language. So, for example, imagine you're writing a text on your phone, and just as you type, how are you, your phone may suggest doing today. And that's a very basic example of a language model at work. But now if you scale that to, massively, where the model doesn't just predict the next few words, but it can generate a whole page of text. It can have a conversation with you, and it's coherent and contextually appropriate to the prompt that you write or the information that you give it. And that's basically what LLMs do, right? They predict the next word, but they do this on a massive scale. And just that concept of being able to predict the next word allows these models to do, really sophisticated things like summarization or having a Q&A with the large language model, because it has the ability to do that.
So how does it do that prediction? Like if I had to peel back the cover a little bit and looked underneath the covers for a large language model, how is it doing that prediction of that next word? Like, what's the secret sauce?
Yeah, well, the way that these things are trained, right? Like when you train a large language model, you basically throw a lot of data at it, right? And then the model kind of figures out these patterns. And the way that these models work, they're neural networks, right? And the neural networks have parameters, and the parameters represent the weights of the model. So, in other words, if I'm writing, how are you, and the next potentially next sentence would be, how are you doing today? Doing today would be the predicted words that come after how are you. Those would be represented in these neurons through weights. And then the model can go through these neurons and go through this path and then figure out that the most likely predicted next words would be doing today because of the weights of that parameter of the models.
So those words are those represented by each of the parameter? What does a parameter contain? And
The
is it just
parameter,
weight, or is it just also knowledge?
actually, the parameters contain weights. They contain weights. They're numerical. All these models are doing are math calculations at the end, right? And they take a word and they convert that into a vector, and then they're able to then represent that word in a numerical format that is then embedded into the parameter. And the parameter contains the weight that defines how much of an influence that certain word or phrase has on the rest of the model.
Okay, but I've heard that the models also contain the knowledge itself. Where does it store that?
Well, it's actually in the weights of the parameter itself through the model. So the model has a numerical version of the text inside those parameters, and that's how it represents language, is basically through numbers and through the algorithms that are part of the neural model.
So let me maybe ask another follow-on question, what Sadab just asked. So when I think about this model and the parameter and the weights, like, where is that actually stored? And let's assume we're talking about Azure, OpenAI, GPT-4. I create and I deploy that model. Like, is there like a database somewhere that contains all of those parameters and the weights? Like, what's actually implemented? And I just talked about OpenAI, but if I'm assuming, however you're going to describe it, is that the same for like a Llama 3 model? Is that the same for Gemini? Like, is there a large language model database with their parameters? Like, what's that physical representation?
Yeah, it's actually actually a very large representation of the neural model that's put into a very large memory vector that's distributed across in our example on Azure, right? So it's not a database. It's actually a very large neural network that's represented into memory so that the model can do the inferencing of the model on the fly.
I guess that's why GPUs and big clusters of machines are so important into large language models.
Well, you raise a good point, and the reason why GPUs are so powerful to work with these models is that when these models calculate and predict like the next word in the model, right, they actually represent words in numbers, like I said. And to calculate these next words, or to predict the next words, they have to do matrix calculations. It's exactly like if you had an image, and these are represented by zeros, ones, and twos. Images are vectors, and on a gaming computer, you would play video games, and you would need a GPU for it to process these images to be able to play your video game, right? And it works very similarly in language, right? Where this language is represented as vectors, and these models have to do vector calculations. And to do that, you need to do matrix calculations, and GPUs are excellent at that because they've done it with images. So now the images are represented like language. So that's why GPUs can process neural models so well, because they actually, all they do is calculate matrices of words, and they can do that really, really well. And that's why they work extremely well with GPUs.
You talked about the prediction. So essentially, they are predicting what are they predicting? Is it just the next word, next token, next sentence, next entire page? And does it know beyond that prediction what it will predict after that prediction? How far can it see?
Yeah, and that gets into a concept of the transformer model, which is around self-attention, and it's a mechanism for the model to be able to basically look back at the previous words to determine what should be the next word or the next word after that. So we can definitely talk more about like the transformer model and how that works in self-attention, because I think it's important to understand how these models work and how they keep context and how they're able to basically have the ability to generate the next word, the next sentence, or the next paragraph. And it has a lot to do with the transformer model and this self-attention mechanism.
Oh yeah, I know about transformers. I used to use them to change my electric load. Is that what you're talking about?
Used to what?
My electricity load.
I don't.
I
I'm
thought
not
you were
sure.
going to talk. I thought you were going to talk about Maximus Prime and those transformers.
Yeah, that's another angle.
Yeah.
Yeah. Well, the thing is, like, the journey of LLMs, it started quite a long time ago, right? Where the development of like traditional machine learning, where in the fields of like computational linguistics and in AI in general, and these fields have been evolving for decades, right? But there's been a significant milestone in the form of neural networks, which I was speaking about, which are systems that are modeled actually after the human brain. So in the mid 2010, advancements in these neural networks were really like center stage and really set the stage for these modern LLMs. If you look at deep learning, what really happens in these models, like they learn through the layers of complexity, which is ideal for handling things like complex human language. And the real turning point for these deep learning models was called the transformer model architecture, which was released by Google in 2017. In fact, there's a great super famous research paper called Attention is All You Need, and that explains the architecture very well on how these models are trained and how they built these neural networks and these parameters and these weights out of these models. This architecture, by the way, completely changed the game by being particularly good at handling sequences of data like sentences in text. If you want an analogy to this, imagine you were trying to assemble a jigsaw puzzle, and instead of looking at every single individual piece at once, you basically focus on a certain part that fit together at that moment for that puzzle. And over time, you start assembling different sections of that puzzle until the whole picture is clear. And the attention mechanism in a transformer model works exactly the same, where it focuses on different pieces of the language puzzle to figure out how it all fits together and how how to make sense of all of the text. And that's how it has the ability to not only predict the next word, but predicts an entire sentence or entire paragraph or potentially an entire 3-page paper, right?
So a question for you, and I'm assuming the paper you're referencing was, from Google DeepMind, right? And the way that they've, kind of coined the transformer. We've certainly come a long way from, I guess, that initial paper and the ways that organizations have created an LLM. Like the state of where we are today is what we see in terms of like GPT-4 or 4.0 or some of those other models. Like DBRX has models. Gemini is obviously there, and you can point to things from Meta. Are each of those models the same structure, or have people advanced, or organizations, have they advanced the way that these large language models are actually designed? And or maybe another way of asking it is, are we moving in a direction that these designs of large language models are taking different approaches to be more efficient? Like, how are we going to get to, the next stage of models that may approach AGI or artificial general intelligence? Are we seeing differences in models? Let me rephrase that.
Yep. Yeah, I mean, like there are models that, you look at GPT-4o, right? Who like where OpenAI has ingested audio in it and video, right? So they have more modalities that they can use, right? So they're trained with more types of data, and they're able to do a lot more things like listen and create audio and even create images and analyze images. And so those, I think there's an evolution where these models start gaining different modalities which allow the model to do a lot more things, and we're seeing an advancement in that, where we had, multimodal models, and now with GPT-4o, we have these kind of omnimodal models that have the ability to do a lot more. And I think we'll get to a point where we'll have this, model that will be able to do everything, but we're just not there yet at this point.
Right.
But then when you think about the architecture of these models, and you look at the transformer model, for example, not all models are created equally. Like there are various designs and architectures on how these models that have their own strengths and are suited for different tasks. For sure, the most widely used architecture is the transformer model. So the majority of the LLMs that you'll see on the market today are mostly trained using the transformer model architecture. But this design, it's favored because it has the ability to generate natural language very effectively using self-attention. However, as the field evolves, there's constantly innovating and experimenting new designs and new architectures. For instance, some models focus on proving efficiency. Some focus on reducing the environmental impact of training these, very large models, or some, concentrate more on enhancing the model's ability to understand context more deeply. Have you heard of a model architecture called the mixture of experts before?
I've heard about it, but I'd love for you to explain it, because it's a little bit obtuse for me in what it is. So what is the mixture of experts? And maybe a follow-on question to that, as you're explaining it, who uses mixture of experts today in their model design?
Actually, if you look at the GPT-4 model, it was trained on a mixture of expert architecture. So it's actually a bunch of transformer language models that are very specialized in a certain domain that actually work all together to actually, they use that to train the model to make them much more smarter. So I'll give you an example. So just from a definition perspective, the mixture of experts, it involves multiple specialized model, and we call those experts. And all of these have different aspects of a task, and they work together to achieve better performance for than just one single model. So I'll give you an analogy. Imagine a team of doctors, each specializing in a different area of medicine, right? And you have a cardiologist for heart issues, you have a neurologist for brain health, and so on, right? And when a patient arrives with multiple symptoms, each of these specialists, they need to evaluate from their expert's perspective to come up with potentially a diagnosis. And what they do is they collaborate to form a comprehensive treatment plan for this patient. And similarly, a mixture of expert model, it uses each expert's neural network and focuses on specific type of data or task. Then it combines all that effort to lead to a more nuanced and accurate model, such as GPT-4. That's how GPT-4 was trained. So in other words, you segment the expertise into different models, and you use that to train the bigger model for the inference.
So
Got
at a certain time, you are only leveraging a number of experts, not all the experts. Is that what you're saying, Simon?
You're leveraging all the experts in the pool that you've created of expert models, and then you use that to train the larger model using this kind of expert pool of models that work together to train the model.
So is that mixture of experts only during training, or is that also during inference?
That's a good question. So GPT-4, it was used for on the training side of it, but those things are embedded within the model, right? So now these models have the specialization that came from these mixture of experts. So when you're using the inferencing, they're actually they're very aware of these experts, segments that are part of the neural networks that they can tap into for specific tasks that are, domain specific or require a certain expert that it was used to train on. And then, of course, there's a lot of work being done on agents. I spend a lot of time on multi-agents and autonomous agents, and we have a lot of customers who take a single LLM. Most customers today take a single LLM and they try to agentify it by giving it an external reality, or by doing things like retrieval augmentation generation, and or giving it things like function calling so that they can take actions. And what you do is you're taking one LLM and creating an agent out of it, right? That's able to do a lot of things and do a lot of tasks. But we're getting into a realm now where customers are taking these single agents and combining them together into these multi-agent systems. And these multi-agent systems are actually very similar to a system, to a mixture of expert architecture, where now you have a bunch of LLMs that are specifically grounded into a specific domain that work together to solve much more complex problems. And so you can see that on both sides, right? You see this type of architecture on the training side of it to make these models much more smarter. But then on the inferencing side, you have you have a lot of customers that use these LLMs and combine them to create this multi-agent architecture that solves much more bigger problems.
I think you just booked yourself on another episode to come back and talk about agents.
I am more than happy. I spend my days on agents, so no
Absolutely. But just on the mixture of experts, Simon, just a follow-on question. What is Mistral model then, that design that they follow? Is that different from how the GPT-4 works? Because they talk about not leveraging all the parameters in one go.
And I'll add something onto that as well. I mean, Snowflake just came out and they were touting, their was it Snowflake Arctic, something like that, and their dense mixture of experts. Is that taking the concept of mixture of experts to the next level? Like, is that the next forefront for what large language models can or should be doing, or is it just one's organization's pathway that they see an avenue for?
Yeah, I think to answer your question, I mean, the majority of the work being done now is on like system of experts. So that's kind of becoming a de facto common architecture to develop model. Mistral is a great example of that. It is a mixture of experts. It's trained with a similar concept as GPT-4, except it's a smaller model, right? They use quantization to reduce the parameters of the model to make them smaller, but trying to keep these models still having the ability to perform a lot of tasks that were trained on these expert model systems. So at the end of the day, they're very similar. It's a very similar approach, and system of experts have been demonstrated through a lot of research papers that they do increase the reasoning capabilities of these models by quite a lot.
Cool. So, question for you. So we know that there's, I'll call it, proprietary models. There's open source models. Are there real differences in terms of the underlying technology? Like we've just been talking about, the mixture of experts, parameters, weighting. Like, what's the real difference between, open and closed models? Is it just about what's being disclosed on the way they build it? Like, what's the real difference there?
Yeah, that's a good question. I think, again, at the end of the day, they're all they all stem from transformer model architectures. So from the core, they use the same type of architectures to train these models, and they use, deep neural networks, and they store parameters, right? On the open LLMs, I think they're usually much smaller, and they can be used. They're faster. They have a lot less latency. But as the name suggests, they're open, right? So what does that mean? Is that the underlying architecture and the training methods, and sometimes even the training models themselves, are available for anybody to use, right? And modify or built upon. So the openness promotes this transparency and collaboration within the community, which allows them to, improve these models on their own, right? So, and in contrast, if you look at proprietary models, they're developed and controlled by companies or organizations that are not necessarily openly shared with the public. And these technologies, the technology behind these models, including the training data and the model parameters, and even in some cases, performance benchmarks, is often kept confidential. And big companies might do this to protect their investment or maintain a competitive edge in the market. Now, if you think about open LLMs, let me use another analogy here. It's like a community garden, right, where everyone has access and can contribute to the growth of the garden and share the harvest. And it's a collective effort, right, where proprietary models are more like a private greenhouse, right, where access is restricted and the owners control who can come in and what can be taken out of the garden. And both approaches, I believe, have their merits and challenges. Like, for example, the community gardens, they foster, a much more wider collaboration, but deals with issues like vandalism, right? Where people could use these things irresponsibly, or they can do things with it because it's open and they can change the actual weights and the parameters of these models, and they can basically do whatever they want with them. Where I think the private gardens, the closed LLMs, they can focus on specific goals and maintain really strict quality control of these models, but they may lack innovation when it comes from a broader community involvement, in my opinion.
Right. It's that whole like crowdsourcing and being able to control that crowd from an
right, exactly. Yeah, exactly.
So let me ask you a very important question about large language models. You ready?
Sure.
Why do they lie? AKA, why did they hallucinate? Like what's up with that?
I've never
They're
heard that
just a
question
reflection
before.
of humanity.
I've never heard that question. Okay, well, so at its core, the issue, I think, stems from these models, how they're built and they're trained. LLMs learn to predict and generate text based on these patterns that they've seen during the training phase, right? And which involves a massive amount of data collected from the internet. And these data sets, they can contain inaccuracies, they can contain biases, or even fictional content. So the model actually, they can't distinguish between fact and fiction. It simply learns by replicating the patterns that it has seen through its training data, right? And LLMs, they operate by estimating the probabilities of what words come next in a sentence, rather than accessing some internal database to fact check itself, right? And we can do that today. We can do that with RAG, where you can ground the model, give it the information that it needs, and that reduces hallucination or fabrications in these models by quite a lot. But the reality is that these models have been trained on quite a lot of data, so they still may have that the ability to not have to create fabrications and create hallucinations. But so, like, I'll give you an example. If you ask an LLM, whether come up with an example here, whether unicorns exist, okay, the model might generate a response like unicorns or mystical creatures, and they're depicted by a white horse with a single horn and blah blah blah, right? And this statement is pretty coherent and it aligns with the common myths, but it doesn't clarified that unicorns are fictional. So if the question is framed expecting factual accuracy, the model might still draw from the more popular or frequent patterns that it's seen in its training data, leading to misleading answer. And that's just how these models work, right? And there are many techniques and prompt engineering techniques and RAG and different approaches to mitigate these models, to ground them, to make sure that they have the ability to reduce the hallucination. But at the end of the day, these are probabilistic models, and they may always produce things that are not necessarily true. So you have to really spend a lot of time doing prompt engineering and doing these other techniques to make sure that they're more deterministic and more factual.
Okay. No,
So,
that makes. Go ahead.
so this hallucination, in that case, is that a feature or is that a bug? Can we control this?
I think it's a feature because it allows these models to be a lot more creative. You know what I mean? And because the thing is, I feel like we spend a lot of time, at least, I mean, all of us here, we spend a lot of times working with customers trying to denature these models a little bit because we're trying to make them deterministic to solve, specific customer use case. But the reality, these things are very probabilistic and they're very creative. If you ask them to write a poem or write something fictional, they're excellent at doing that. So I see that that's something very powerful that these models should continue to do. I definitely see a point where there will be models that have the ability to fact check and have to be able to provide truth. But I think that probabilistic nature of these models and the reality that they can hallucinate actually makes these models really, really fun to work with, except when you're trying to do something deterministic and you're fighting with prompt engineering, trying to make them do what you want. But I think it has its place, and I think I don't think it's a bug. I think it's more of a feature of the model.
So speaking of making the model do what you want, you already mentioned things like prompt engineering. You mentioned like retrieval, augmented generation, or the RAG pattern, but we hear a lot about fine tuning. I know that fine tuning is expensive, or at least expensive to do in terms of time and or resources as far as compute. But if you had to explain what is fine tuning and the importance of it, within 2 minutes or less, what is fine tuning and why do it even in the first place?
Okay, yeah, that's a good question. So fine tuning, it's actually a pretty powerful technique that is used to adapt these pre-trained models to perform specific tasks or to improve the performance of these models. Fine tuning is it's not a new concept. It's something we used to do in traditional machine learning when we used to take vision models and we used to adapt them to have the ability to detect, other objects or things like that. It's a mechanism called transfer learning. Fine tuning is very similar, where you actually go into the model and you change some parameters of the model so that it becomes really good at that specific task that you're trying to make it do. I have a lot of customers who want to fine tune LLMs to give them more knowledge, but in my opinion, that's not really the right thing to do. It's been pretty much how can I say I mean there's a lot of benchmarks and different research papers that suggest that just doing retrieval augmentation generation to provide these models with new knowledge is very effective, and doing things like in-context learning to get these models to be grounded with new information is really powerful and it works really well. So if a customer is trying to fine-tune a model to give it new knowledge, it's probably not the right approach, because fine-tuning is the ability to teach the model on a new task or pattern. Okay, that's really the core of it. When you and what I mean by that is an email has a certain structure, right? It has a pattern. You have a header, you have a footer, you have a CC, you have a to, and you have an introduction. It follows a certain pattern. If the model, for example, an LLM did not know how to write emails, you can teach that. You can teach it that pattern because it's a structure and it's a pattern, and you can do that by fine tuning. You can teach it how to write emails. You're basically teaching it on a new task that it necessarily didn't know how to do. And I feel like those are really good scenarios where you try to adapt the model on these new patterns, on these new structures. But applying using fine tuning to apply the model with new knowledge is probably, like I said, is probably not the best approach. I'll give you an example, another analogy here. Imagine, you bought a car and that's already been driven by somebody else, right? And it works fine, but you want to adjust the seat, tweak the mirrors, or even fine tune the engine settings to better suit your driving style. That's somewhat analogous to what's happening during the fine tuning of an LLM. So the LLM undergoes a general training phase where it learns from a vast amount of data, and it observes these patterns such as grammar and information. And this phase is like a car being tested and adjusted by the manufacturer to ensure it runs and it performs well under certain conditions. However, just like with the car, there might be specific needs or preferences that the initial training didn't fully address. So, for example, I live in Quebec, right? And we have really a lot of snow, and sometimes cars are not, fine-tuned to drive in this snow. You need, winter tires, you need a good heating system in some cases, and, you need to adapt the car so that it can drive well in winter conditions. So fine-tuning is exactly that, right? You are fine-tuning the model so that this car that already existed now can operate in winter conditions, so I think, I think that's, to me, that's what fine-tuning is all about. It's teaching the model a new task or a new pattern,
So basically taking a Pinto and trying to make a Ferrari out of it, that's a really expensive proposition. And that's
Yeah.
why when you want to think about fine-tuning lightly, because you're not going to go from an inexpensive car to a very expensive car. It's about just, like you said, putting on new tires rather than trying to do a whole overhaul. I like that.
That's right.
I like that analogy.
Yeah, exactly.
That's a good explanation, because what I found is, Simon, like AI has existed and people kind of like try to relate it to the older times where every single data science model had to be trained, and they still think in that way. What people, I think, mistakenly believe that, okay, if this LLM has to work with my data, it has to be fine tuned. And that is so wrong. What are
That's
the,
totally true.
like, how would you say to that older population or the older understanding of them to realize that knowledge is not the reason for fine tune? It's really, but what are the ways in which do you include the knowledge in the LLM's outcome then?
So, sorry, two questions there. The first question was,
Yeah. So in the terms of, let's say, like generally people think that just to interact with my data, I need to teach the LLMs about my enterprise knowledge or my documents knowledge. Is that why I should fine tune? And the second
yeah,
question is that if not, then how else do I make sure that this LLMs know about my data and can answer me based on those data?
right. I see what you mean. So, you're absolutely right. When when ChatGPT first came out and we had an influx of hype and people knocking on our doors to work on ChatGPT use cases with them, it seemed like everybody just wanted to fine tune them, right? Because they came from a traditional machine learning background where you basically take data and then you take a model and then you retrain the model and you change the parameters of the model to adapt this model with new knowledge. But the reality is that it's not really how these models work. I almost feel like if you do that, it's trying to like hit a nail with a broom. It's just not the right tool at all. It's not going to work, The way to give these models, new knowledge is usually done through things like in-context learning. And what that means is that you actually ingest that new knowledge into the prompt. These models have actually a very large context window now, some up to 128,000 tokens, and a token represents about 4 characters. So quite a lot of data that you can actually ingest into the context window of a model to give it new information. And what happens here is that the model is able to take that information and reason over it and apply that new information through the existing parameters of the model to be able to come back with an output from that information. you're actually not really even changing the parameters of the model itself. It's using the parameters of the model that already exist to basically reason over that new information to come back with an input. That's the best way of doing it. And retrieval augmentation generation takes that a step further, where it automates the process of you retrieving that information from a vector store or a database and bringing that in dynamically into a prompt so that it can reason on new information. That's the best way of doing it. And you know why? Because first of all, fine-tuning a large language model is really expensive. You got to retrain. Like, imagine retraining an entire GPT-4 model. That's going to cost you a lot of GPUs to retrain an entire model with new information and having it retrain itself, recompile itself, and changing all the parameters. It's a very expensive process, and it takes a lot of time. In-context learning is real time. You bring data in there, and you're not changing the model whatsoever. So you're not running a retraining job, nothing. You're just adding new information into the context, and the model reasons over it and is able to use that information to base itself on. And I think it's much more powerful because you don't have to retrain a model. It's not that expensive. And then you could use retrieval augmentation generation to automate the process of bringing that new data into the model in real time.
Sounds good.
Perfect.
Yeah, Simon, I think the more that we go through, the more questions that I have, and we could probably spend another hour or two and probably not get through all these things. So I wasn't kind of joking before when I said we definitely want you back on to talk about, any number of topics here. So
Yeah,
it's like
I'll take you up on the agent one. I'd love to do that one.
Yeah, I think I'm looking at your whiteboard behind you, and I think I see something that says agents. So
yeah, it's a single agent architecture with a multi-agent architecture on the bottom for a specific media and entertainment company.
So yeah, definitely would love to get you back, talk about agents and a bunch of other things. So just wanted to thank you again for jumping on with us today and sharing your knowledge.
Thank you. I really appreciate it. Thank you for having me.
Thank you so much, Simon.
Welcome.
Bye-bye.
Thanks. Take care.